Thank you.
Thanks. All right, so my main thing is to just try and set the scene for the week. So thanks for coming, first of all. It's great to be here. And it's not entirely a code-focused workshop, so we're going to have lots of different science. And the main point of the workshop, actually, is that we all talk to each other and find the links between the things we're doing and the common factors. So if there's nothing else that you do this week, the main thing is to talk to each other and to find the common projects in common. But we're going to try and deliberately structure that in the afternoons as well. Beck will say a bit more about that later. We have a bunch of ideas planned. So first of all, what's new? This is the first workshop back in 2018. You can see there's a small group of us. There's some faces who are here virtually. So James, I think you're here. Are you here, James?
Yeah, I'm here.
He's here, yeah. Joe's here. Terry, I think, he's being represented today. I don't know if he's here, but there's a lot of people who aren't here anymore, but, whose science we're going to talk about today. And I see, like, the next generation here as well of people who are, like, the students following, for example, like Tom Reichert. I can see a bunch of people on common envelopes, and Nord. I can see Stefan from the group. So it's interesting to see, like, at the 2018 European Users Workshop, I actually only spot 3 people. I can see Benedetta up the back there. Dave Liptai, I don't know if he's here today, but he certainly finished his PhD quite a while ago. And Martina, you snuck up there. But apart from that, everybody else I think is new. So it means we've got one thing that's new is, like, a lot of people here are new to kind of science applications we've been doing or are following in the footsteps of other people. So that's great. Actually, the last workshop we had was in 2020, which is interesting because it was like the last thing before the world stopped. I mean, Benedetta, I think, was like the last visitor to leave, I think, before everything shut down. So that was held at a kind of interesting time in 2020. But you can see, actually, the delay has meant there's a lot more people here because we haven't gathered for a while. So it's really nice to get the world back in order and be back in action. All right, so just because a lot of people are new, I was going to just go over some things I already talked about in previous workshops, but what the original kind of motivations were, why we needed a new code at all. So SPHNG was a code originally from, like, Willy Benz in the 80s. It was a code developed for, like, the formation of the moon scenario, and it was developed by Matthew Bate further, who was kind of my mentor at the time. But it was written in, like, really old Fortran. And to be honest, if you look at the errata that we published around 2007 or something, that was when I realized I have to stop wasting my life on this. Because, the biggest thing when you're doing things computationally is you spend a long time looking for bugs. And so one of the motivations is just to spend less time looking for bugs and have something which is tested and works. The other thing is, like, the main public codes available for smooth particle hydrodynamics in astronomy, which is a particle-based method for simulating fluids, are usually doing for doing cosmology. And a lot of things that you care about in cosmology are really things that you don't care at all about in star and planet formation. So, for example, we rarely use periodic gravity, for example. In fact, never have and never will. We don't really use dark matter most of the time. So a lot of the effort is put into, for example, very fast gravity solving, but not much, or recipes for things which we don't really use. So they're not very well suited to the kind of physics we're interested in. And so we were interested in physics relevant to stars and planets. And I also had a bunch of other, I got frustrated because we're originally in the maths department at Monash. Joe Monahan was one of the founding members of the maths department here at Monash, I think back in the 60s. And so that meant what we did as a group is a lot of algorithm development. And I got frustrated because you'd make these, like, better version of doing things and you put it in the literature and then no one would use it. And I realized after a while that, like, no one's going to do that because it actually takes a lot of work to look at what someone's done, implement it yourself, and then you don't get any credit for it because it's someone else's thing. So I realized, actually, if you want to make these kind of algorithms available that we develop a lot in the group, you got to just give the code with everything working and let people use it for science. So that was basically what we needed is a public code that stays up to date with the kind of algorithm development that we do in the group, so that it's just usable out of the box for science. And that's, I think, for a lot of people's experience of using Phantom is that you've been able to do some cool science by using it out of the box, but maybe you want to do a little bit more. All right. Moving on. Low memory footprint was also an initial consideration. That's where the name Phantom come from, because it was supposed to be like so low memory you never see it. Anyway. So the initial things, I didn't try to do everything that we used to do in the other code straight away, but one of the first things we did was this comparison project on supersonic turbulence, which is super simple because it's just gas, it's isothermal equation of state, and it's periodic, which is one of the things I said we don't use, which we don't use actually for anything other than this problem. We never use periodic boundary conditions again. But it was, simple enough, and the code was fast enough to do lots of, pretty high resolution pretty easily. And it meant I could do at least one problem that wasn't in SPH and G, and that basically looks like a molecular cloud. So good. The other thing that SPH is really good at is because there's no preferred direction. So because particles can just move in any direction and the code conserves angular momentum perfectly, means things like orbits that are misaligned in different directions are really accurately done. So things like warp disks is a very natural thing that people with Eulerian codes really shy away from, these kind of problems, because they really mess up the scheme if it's not aligned with the grid, or if it's going sideways on a Cartesian grid is one of the worst things you can do. So whereas in SPH it just doesn't matter, so you can do things like warped disks or eccentric or misaligned flows. So this is a nice example of disk tearing, which was a phenomenon we sort of discovered, and Rebecca did her PhD in this area as well. So this is how if you have a spinning black hole, it will warp material into a different plane because material wants to precess. But the precession is highly variable as a function of radius. So the inner material precesses much faster than the outer material. So you can end up ripping a disk into pieces, which is cool because when we were doing this at the time, we were like people in a maths department going, this is a cool phenomena. But Chris and Rebecca also worked on the fact that you can do the same thing with a binary. So you can replace the black hole with a binary, put it in a different plane, and you could get the disk to tear into these separate rings, which is amazing because it was observed in 2018 around the triple system GW Ori. It's got these rings that are like all misaligned into different planes. I don't have a picture, but I never thought that actually within 6 years we'd go from this crazy idea with a code to like actually something that's been observed. So that's pretty cool. Oh yeah, so this is the binaries version. So you can just put a pair of sync particles, but this is the first time we actually used sync particles, which is an old idea that if you want to represent stars that accrete material, so there's a boundary condition on those where they eat gas, but then you can replace your spinning black hole with a binary, and the same phenomena basically takes place. And as I mentioned, that's been observed. Do you want to keep going? I've got lots of movies basically. But so sync particles, so the physics came slowly. We're starting from basic gas dynamics and working upwards. So at the time, this is there's no gravity from the disk itself. So there's gravity between the stars and the gas. So the gas is feeling the potential of the binary, and the binary is acting on the gas. But there's no gravity of the gas on itself, which is what we call self-gravity. You see, yeah, it looks like a blender basically when you have the binary version. So magnetic fields is something we did a lot of development on as well. And James Worster is going to tell you about the latest on this kind of stuff. But essentially, magnetic fields in SPH was a kind of old and hard problem, and it's what I did my PhD on. And so we made some breakthroughs in 2012 based on something that Terry Tricot, you there, Terry? Nobody's student is.
Oh, sorry, I am here.
He is here. There you go. So Terry worked on fixing the div b equals 0 constraint in MHD, and that meant we could sort of do production runs of magnetic fields in things for the first time. So that was a natural thing to go straight into Phantom, and it meant we could do some interesting applications, like, for example, this is a simulation of the early stage of star formation, very simple sort of model where you just have a rotating sphere kind of collapsing, but there's a magnetic field threading the cloud. And I was very happy for the first time to reproduce phenomena like jets, which we knew from the 90s from like star formation, but this is jets from a very early stage of star formation. And obviously you can't produce a phenomena like that without magnetic fields. So magnetic fields are good. The other thing that the old code was basically designed for was this kind of star cluster formation calculation. So you take a turbulent cloud, you let it collapse under its own self-gravity, and you try and form stars. So we implemented self-gravity around 2017. And David Liptai, we published a paper. I think that was the first paper where we used self-gravity in the code to do a proper like molecular cloud collapse to form stars. We actually haven't done a lot of that since. And one of the reasons is because radiation development kind of stopped. So one of the things that became really important in star formation is that, so here we just set the temperature as a function of density. But one of the things that's really important is the stars obviously make the material around them hot. And that stops the material collapsing to make new stars. So there's no, in these kind of calculations, we were doing a certain experiment, but there's no feedback from the stars. And that's one of the things I'm going to talk about in just a second about the new developments. So MHD progressed rapidly. So James Wurster did a postdoc here working on non-ideal MHD. So that's when you've got these effects from partial ionization, like ambipolar diffusion, which is drift between the ions and the neutrals. Hall effect, which is a drift between the ions and the electrons, and ohmic diffusion, which is just drift. It's just diffusion of current. So James spent a lot of time implementing and testing all that and getting it working, and then we applied that to lots of problems in star formation, which James will tell you about hopefully later in the week. The other thing that happened was Guillaume Leb, who I think some of you know. We worked a lot on trying to formulate methods for dust and gas. So the classic formulation of dust and gas is you have this drag term between the gas and the dust that exchanges momentum. So that's literally from dust grains, gas hitting dust grains and then exchanging momentum. Looks benign, but there's lots of little problems with this. In particular, that this drag coefficient can be infinite. So having infinity on the right-hand side is usually a bad idea. So there's lots of things that came along with that we worked on. So in particular, you can have these constraints like this stopping time, which is inversely related to K. And the stopping time can be either 0 or infinity. So you want to be able to handle both regimes really well. So one of the things we did was we could reformulate the same equations. So it's actually just the same equations in a different set of variables, but you get it as a mixture, and then you get these sort of separation terms rather than the terms that try to drag each other together. So you get this sort of exponential decay of differential velocity between the dust and the gas. But you can make a further simplification, which is if you've got small enough dust grains, this equation set simplifies even further. So basically just your regular fluid equations, conservation of mass, conservation of momentum, and this kind of diffusion equation for the dust fraction. So that's like a really simple way of doing small grains, and small grains are really important. So they drift apart from the gas because of the pressure gradient. And obviously if the stopping time is 0, that means they're completely stuck. That means gives you a constant dust to gas ratio. So that's something we know from the interstellar medium, how that works. So all this stuff was new at the time. This is sort of 2014. And it was well timed because that's when the ALMA telescope came online and started taking pictures of protoplanetary disks in gas and dust. So one of the things we immediately knew how to do was this kind of gas and dust mixture and simulate a disk and see what happens. And one of the really important things at the time is just when you're taking pictures with millimeter wavelengths with ALMA, you're looking at the kind of dust disk, which is this settled disk in the midplane, not the kind of puffy gas flared disk. So we made the pretty sort of easy paper. It was obvious in hindsight, but you just put some planets in that, but you're simulating both gas and dust. And of course, the planets make these characteristic wakes in the gas, but in the dust, you just kind of make rings because the dust is like settled into this thin disk, more or less like Saturn's rings. So this is kind of obvious, like everyone's going, oh, well, where are the spirals and like, where are the, how can there be just rings? And maybe there's all some crazy mechanisms. We're like, no, it's just the dust settled. which you could do a pretty good job of. The other thing you could do by simulating each of the grain size. Now we did this a little bit painfully at the time, like doing each simulation per grain size and then stacking them all together afterwards. But then you could make sort of synthetic observations by sticking it through RAT-MC3D, which is our favorite radiative transfer code. It's not here, so we can insult Christoph. But make synthetic observations and really do that. So that started on this whole journey, and that's turned into a lot of interesting science in the last few years of just being able to simulate the dust and gas mixtures. And I can see some people here who are, we're starting to apply this to another area of science now, which is in the area of AGB stars are basically like big spherical disks. So they form dust, and they have like dust that's it's formed in the winds of AGB stars. It's where the dust in interstellar medium starts, and we observe them with ALMA. So there's a new, really interesting area of application. There's a couple of people here who are going to talk about that later today, I think. So that was all actually before the code went public. So code went public in 2018, and so there's a bunch of stuff in a very long paper that no one's read, probably. Anyone read the paper? Cover to cover, yeah, all 80 pages, yeah. Okay, maybe it helps you sleep at night, I don't know. But a lot's happened since then. One of the immediate things that happened was, so Christoph arrived, and when he arrived in the department, this was not long after. But, so the idea of like this idea that planets would make these gaps in disks was not just a fiction, but you could actually do a bit more than that. So not only do you get observations of dust emission, but you get, Doppler shifts from molecular line emission in these protostellar disks. And so you can map the flows. And what Christoph says, well, there's a funny little wobble there that doesn't quite work. And we made this pretty simple model, really. You just stick a planet in a disk and like, what does that look like? But what does that look like involves obviously post-processing the snapshot with a radiative transfer code, making it appear in the right spectral line with the right Doppler shift to show you what you're looking at. And so that became like a real pipeline where we could basically directly take the snapshots from the code, run it through MCFOST, which is Christoph's Monte-Carlo radiative transfer code. In case you look at me blankly, so Monte-Carlo radiative transfer, you just bang photons around randomly, and they end up telling you what the temperature is, and then they leave, and then you just place the camera and you catch the photons and you see what you're looking at. So basically the underlying model is something like this. So this is what you get out of the fluid equations. You get a simulation where you've got densities and velocities and things for the flow caused by this planet, and you stick that through your radiative transfer code, and you can get synthetic observations of that. And so we learned, we did that to learn, okay, we've got a planet here. It seems to match just having a planet orbiting in the disk. And we can use the simulations to measure the mass. And so this kind of became almost for us like a little industry where we could do this sort of thing repeatedly. And it's one of the tools we want to offer to the AGB people is like, we've been doing this for a while now, where we're doing this kind of comparison with ALMA and backwards to modeling and back and forth to try and figure out what's going on. And the game we've been playing is to look for companions and planets, which seems to be the same game in AGB stars. We're looking for companions and things. So it's a really great, I think, be a really great sideways step. Okay, so the other thing, so this was all done with a single grain size. So the other thing we've been working on since then is to be able to do all the grain sizes simultaneously in the code. So this is still, it's not perfect, but so Mark Hutchison, who did his PhD at Swinburne and then was here for a year, we worked on what we call the multi sort of small grain method. So you could have this mixture model with the set of equations, but you have an epsilon per grain size. So this is a single simulation, but you can see this is like a section of disk, and you can see the large grains settle to the midplane and the small grains stay kind of suspended at large scale height. And Daniel Menteplay in his PhD also worked on the multi-large grain. So basically where you have two separate sets of particles representing the grains, then you'd have a set representing each of the large grain sizes. And the black lines here are an analytic solution. So you can see that there's drift of the grains. So this is the radial velocity. So the grains are drifting inwards, but some of the grains drift outwards because they're stuck to the gas and the gas is like flowing out. and most of the larger grains drift inwards. But you can capture those effects simultaneously, which is really nice. So I wouldn't say there's any spectacular application of that, but it does make a lot of things we're doing a lot easier because you don't have to run multiple simulations. So dust growth came along not long after that. So Stefan's going to tell us more about this in the week because he's been working on it as well. So this is basically have a mean grain size per particle and you can evolve it with time. So certainly this is an interesting area of like collaboration as well, because dust growth is very similar to the dust formation that we've been trying to do in the common envelope. So I'm looking at Miguel here, but he's asleep. But so there's a connection there to be made about dust obviously when it's born, it starts small and then it grows with time to make these larger grains. And so Arnaud has basically implemented this. We haven't had a lot of applications yet, so Arnaud kind of finished and he's left it to the next generation. So Stefan, I think, is carrying the torch there for dust growth. But it works with both of the dust methods implemented in the code, so dust as particles and dusts with this mixture model. And Stefan will tell us more. There was another issue at the time, is that there was an accuracy issue with using the separate sets of particles to represent really stuck grains, which we published a fix for in 2020. And again, you don't really need to know because you don't have to read the paper and then put it in yourself. You can just use the code, right? It's in. So that's kind of what the thing we were trying to do is really, when these new things come along, we can just put them in and you don't have to worry about it, rather than like wait for Gadget which is kind of the situation we were in back in like 2000 and dark ages. But something like this, so stellar flybys is a really nice example of using, different grain sizes to understand, in a flyby, for example, how do the grains of different sizes respond? This is Nicholas Coelho's work, who's here in the front row. And this is the sort of thing that I think we did this actually with separate simulations at the time, but it's the kind of thing that you just could do in one simulation now with the multi-fluid scheme. But it's a really nice. Actually, this became very topical because one of the things we've learned with ALMA is that stars, well, you already knew, but stars are not born in isolation, and there's lots of like fun interactions that go on in the early phase of star formation. Again, it's sort of one example you might not have noticed, but one of these planet detection things, the really obvious thing you want to know is, the small grains are pretty stuck and the large grains are give you these quite wide rings. So, you can put them in the same simulation, but when you're trying to reproduce these kind of planet-induced structures, you'd like to know what the Stokes number is, which is basically the ratio of the stopping time of the grains to the orbital time of the gas. And you want to know how stuck the grains are. So this thing on the right is an observation of this disk HT 97048. And these are just simulations. Well, it's the same simulation, but with 3 different grain sizes in the disk. And you want to know, well, so that's if you take what we thought was the right grain size, you see that the Stokes 1 grains would give you a gap that's way too wide. And so we want to learn from this that we actually think the grains are more stuck. So you basically slide this whole thing along until it works. So we have a parameter called fluffy, which is like, how fluffy you want the grains to be. And I'm looking at Rachel here because Rachel Harrison's just arrived, who's an expert on like all things dust grains and polarization. So one of the things we've learned from trying to do this is we think that grains are not spherical, which is pretty obvious. But we'd like to understand this a bit more about, we have a spherical prescription for how the drag works, but there's lots of interesting physics there to unplug. Another simple example, so this sort of planet hunting business that we've been on for the last 10 years. So IMLOOP is this big spectacular example of a circumstellar disk in scattered light. I don't know, when I was a student, I'm looking at Joe now, I never thought I'd see images of disks like this. It's just so obvious what it is that it's so people still debated whether the stuff around young stars was in the shape of a disk until Hubble took those pictures of the silhouette disks in the 90s. There were serious debates about whether it was really disks or whether it was something else. And so the idea of accretion disks was still kind of controversial up until then, at least around protostars. But it's pretty obvious that that's a disk and that But what's less obvious is what's in it. So you might not think there's anything special about that image. But again, if you look in the kinematics, so if you make the channel maps that you see in spectral lines with ALMA, then you see all these different material in the disk at different wavelengths. And you can see all these like funky little structures in it, like little traces of spiral arms. They look like something locally is disturbing the gas. And you can make a model of this just like we've always done. And you can reproduce all these little bumps and wiggles with, again, just a simple model, like maybe there's a planet in there. And you can see these little bumps in the kinematics that we can really reproduce quite easily by this pipeline of basically forward modeling. You do a hydro model, you model it forwards, see if it looks like the observations go backwards. But again, the multigrain comes into this because we can compare directly with the millimeter emission. So we're arguing that this spiral arm that you sort of see, the spiral structure, is just this planet wake traced in the millimeter grains. So this is something we did just last year. But also you want to reproduce these really small grains that are stuck to the top of the disk. And so that's that other grain size. So I think we used 11 grain sizes in this calculation, but just they come for free. So it's pretty easy to do. And that means you can also reproduce the scattered light emission really well. And you can actually see the planet wake here, which you may not have noticed in this picture before. But you can see the little spiral stuff from the planet traced in the upper layers of the disk. So again, that's just like an application of the multigrain stuff, which you probably, I mean, it's pretty buried in the paper, actually. I don't think we really talk about it, except it's maybe mentioned we use 11 grain sizes, blah, blah, blah. Well, I don't think we showed any actual pictures of the simulations because we just showed pictures of like synthetic observations. But it is in there and we do use it. So the other thing that I guess we worked on the last few years is this coupling between the two codes. So MCFOST is really fast at this post-processing kind of business. And one of the things that it does is obviously you shoot photons through your disk and that tells you the temperature everywhere. But then what we normally do in like disk simulations is we say, well, we'll just prescribe the temperature as a function of radius, which is stupid, right? We've got a code that tells us what the temperature is and it takes like 10 seconds to run. And if you keep poking Christoph, it gets faster and faster. And so we thought, well, the obvious thing to do is like just actually couple these codes so we can call the radius transfer during the calculation, bring the temperatures back, and then evolve the simulation further so that it's all self-consistent. Now, the temperature also sets this pressure scale height. So obviously, if you change the temperature anywhere, you're going to change the geometry of the disk. And so it takes, you have to be careful to do it all self-consistently, but we burn through a lot of PhD students, basically. Some of them are here, Ellie. But Daniel's now at the Bureau of Meteorology. Sergey's working in business software. But, in trying to get this to work, a fair bit of effort was expended trying to make it all slick and happening and work, but it basically does. We still haven't published a methods paper on it, but we've been using it for a few things. First application was actually one with Rebecca, who I think was visiting at the time. I said, yeah, someone's got to use this stuff. But the really obvious application is where you got more than one radiation source. So if you've got two stars that are radiating the disk, and if there's a misalignment or something, then the temperature is not just going to be an obvious function of radius. In particular, so this binary tearing scenario where you process the inner disk into a different plane to the outer disk, there's a lot of interest in the shadows being cast by these. And so we could do this live in the simulation where you process this inner disk into a different plane and you can see these shadows and they kind of rock around because of this precession, which is not obvious, the way they would just rock backwards and forwards. It's obvious afterwards, but it takes a while to think about why they go backwards and forwards. You can think about that, or you can ask Rebecca later. But it's just a nice example of doing temperatures live in the calculation with feedback between the radiative transfer and the simulation itself. So another application of this has been with Ellie's PhD, Ellie will tell you more about it. But the other one that's obvious is, again, we've got some binary, so there's two radiation sources that are setting the temperatures. And here what we wanted to do was have some feedback between the accretion and the luminosity of the stars. So most protostars, the accretion luminosity is higher than the stellar luminosity. So if you start accreting gas, you're going to get bright and you should, start radiating more stuff back out. If we got audio here, no. Ellie, you can do the audio version. But basically, this little guy grabs material from this disk and then starts accreting like crazy. And so this becomes very hot and very luminous. In fact, so warm that it starts to melt dust. And it all happens very quickly. And Ellie will tell you a lot more. But one of the things we think is this is a really good explanation for is in F Orionis, which is well, it's a star that's the name of a class of things. But F Ori is a binary, and it looks like it's had a flyby just recently. And it's the little guy that's actually the bright one in F Ori. But Ellie will tell you more. But again, this the physics here, or the new capabilities, is that we have this live radiation feedback between the Monte-Carlo code and the SPH code, and so we can get the temperatures updated on the fly in this kind of complicated scenario. So radiation's been a long story for me. Actually, let me go back a step. So basically, I procrastinated for many years. So doing radiation diffusion, which is what you might think of in stars. So, you know, you've got nuclear energy source in the middle, radiation like slowly diffuses to the outside and then escapes. So in disks, you know, really that should happen really only in the mid plane, but in the upper layers, you need some kind of boundary condition. So in Sergey's PhD, we were mucking around with trying to use MCFOST to only set the temperature in the top layer of the disk and then do some kind of radiation diffusion in the middle. And what I was trying to avoid was having to take these very small time steps when you're optically thin. So that's a common problem with doing radiation. Basically, we didn't avoid it, and we did a sort of circuit round. So one of the things we tried was this technique called super time stepping, which is a way of supposedly doing diffusion equations without having to take small time steps when the diffusion rate's high. But actually, we got to some fundamental issues. Even if you take the simplest diffusion problem you can imagine, just a ball of material, that ball is a technique called diffusion of a Gaussian blob. Then you get these sort of oscillatory things developing, which are like not real and bad. So super time stepping was a great hope. But Sergey showed he got it back to a real simple problem. Like we didn't know what was wrong with it, but we got it back to a real simple problem showing what was wrong with it. And so at that point I went, oh, okay. So there is a really complicated implicit scheme, which is implemented in the old SPH code, which is Matthew Bates' smooth particle hydrodynamics code for star formation. But I basically procrastinated it. And eventually I just called Matthew, I think towards the end of last year, and said, can we just copy it across? And he said, yes. And so Mike spent about 6 months of his life copying this thing across. But so we've done basically a direct port of this thing now. So it's really quick, thanks to work involving Joe back in a coffee room in Exeter. And this has just been merged and available in the public code. So this is brand new in the last couple of months, but basically means you can do this kind of thing really quickly. So this is just a shock. So you've got material coming in from the left and right, and stuff collides and gets dense. And if you allow radiation to be trapped, then the temperature will also rise. And if you allow the radiation to leak, so if you let the opacity be low, then the radiation will just leak out and give you something like the isothermal solution. So we can do all this pretty quick now. And I know there's a bunch of people interested in this. So everything that we've ever done in SPH with radiation can now be done in Phantom as well. And in particular, this is relevant to the insides of stars. So we're interested in doing nuclear burning, slow diffusion to the outside, and then release radiation, but also star formation as well. Common envelopes is a big new area. I won't show you this movie again. But the big thing that we've been working on is using these real equations of state, so taking account of radiation pressure, ionization, all kinds of things. And that means we can do real stars with the real physics of stars pretty well. And we've got good at this. One of the things we've got good at is like taking stars from stellar evolution, sticking them into code, relaxing them. So we have this kind of new approach to doing this, which is, okay, the mapping is straightforward enough, but you take a random placement. You fix the temperature profile during the relaxation so that it doesn't change the structure. And then you do this, what we call asynchronous relaxation. So you relax the outskirts and the middle at the same rate, basically. So it's really cheap instead of, so typically the time scale of time steps would be much smaller in the middle than the outside. So this is 6 orders of magnitude in density difference, and they're all parts of the star relax at the same rate. So it's pretty quick. And it's very effective. And it means basically you can take stars and do what you like with them afterwards. which is great. All right, I'll hurry up. Stellar winds, dust nucleation, you're going to hear some more of this week. Miguel's here. Luis is going to be online, I think. But some of the Macquarie group have been working on basically trying to form dust. And Lionel, I think you're here. Saw you before.
Yeah, I'm here. Hi,
Yeah.
Daniel.
So you can ask Lionel as well. So there's a lot of work over many years. But the idea is, below 1500 Kelvin, you get to the situation. So there's this supersaturation ratio where dust will form in your stellar wind. And so that happens very commonly in the out parts of AGB stars. And when dust forms, it's basically a really good trap for radiation. So this is one of Miguel's simulations you'll hear about later. But basically, the temperature's dropped and the dust has formed. So this is the actual live nucleation in the code where you can see the dust shell forming. And the dust shell is exactly just like a Dyson sphere. So a Dyson sphere is like when your alien civilization wants to capture all the radiation from the star. You build a big sphere that's opaque. So if you do that, basically that's what you've built here. It's this opaque shell that's going to catch all the radiation from the star and just go whoop and accelerate that shell like hell. So it's really good. I mean, it's basically a mechanism for accelerating winds. And it's really nice to do this in like real calculations. Couple of more things you hear about. So there's lots of people interested in tidal disruptional events. So you take a star and you whack it around a black hole. We've done this with various approximations previously, but the new thing in 2019 was this GR version of the code. And Spencer's going to tell you a bit more about it as well, but also FITS and MEGA. How long have we got? -2? Yeah, all right. Yeah, so a lot of work in progress on tidal disruption events, but basically this is done in the Kerr metric in full GR, so there's no approximations involved. And we're interested in, again, going to match observations all the way from like first principles simulation to real observations. I think we're nearly there, promise. Okay, so summary, like there's lots of recent significant capabilities, and I probably haven't covered them all, but they include this deep coupling between Phantom and MCFOST, multi-grain dust growth, live Monte-Carlo radiation, implicit radiation diffusion. Stars have got we've got a lot better at modeling stars, GR's in there, dust nucleation, wind driving. And what I hope to hear this week are lots of other things that we should bring in and do as well. I'll just take a minute just to say, so the idea for the afternoons, which we'll talk a bit more about, but this is some pictures from I think the European workshop where they have real blackboards. But we just kind of, had a bit of a brainstorming session about things that we wanted to kind of do together. So that's kind of the idea for some of the hack sessions, is to find some common overlap, little pieces that it would be useful. So for example, one of the things we did here, Stokes-based choice of dust method. So it used to be very manual, the way you would like choose how you should simulate different kinds of grains. So we made a sort of little automated thing that would kind of do the work for you of deciding when you should use one method versus the other. I think that was definitely an outcome that it was very useful from that workshop, and it goes on to be useful for many years. So I think this is the idea for the afternoon, is we do something like this, and then, we've got some little mini projects. And for most of you, you probably, well, some have and some haven't. There's various levels of having dived into the code, but the idea is to get your teeth in a little bit deeper than it may be of none. So if your depth is none, the idea is to get to some. And if your depth is deep, the idea might be to, do something deeper. But the idea is to exchange and learn from each other during the week as well. That's all from me. I'll hand over. Thanks, Beck.
If anyone has one burning question, we've got time. I have actually read the Phantom paper cover to cover, so I don't have questions.
How do you make, when you have the cloud collapsing, how do you make the jet wiggle in your simulation?
We don't make, it's physics. I don't know. Why does it wiggle? Well, essentially, I think because you get very toroidal fields. So you mean this kind of thing? Yeah. So this kind of thing. So these jets are launched by this kind of magnetic tower mechanism where you basically wind the magnetic field into a spring, and then it kind of grows one wind at a time and then pushes this kind of big tower of material up. And so that big tower of material with a toroidal field is very unstable. So it's very wobbly, unstable. So I think that's the reason it's flowing out, but it's wobble unstable sideways. Okay.